Thanks for the introduction. So I changed my title a little bit to include more work I previously did. So now the title is towards the sustainable perovskite photovoltaics, and it's all about how to handle the lead waste. So actually, I should put this Linköping University logo here because most of the work actually were done in Linköping University. Yeah, so go next. Yeah, so my work mainly focus on the perovskite photovoltaics, and I have to say it's now the most efficient thin film photovoltaics. So okay, it's already outdated. Now the certified efficiency for perovskite photovoltaic is over 27. So it's very efficient, and also the stability actually now is kind of certified or tested by the most of companies in China, in Europe, in the USA, that the real product has been tested, and the stability is kind of increasing quickly. So based on the high efficiency and the improved stability, there are so many efforts from the commercial side to trying to put this perovskite solar cell to the market. And it's just some typical example for the how many companies are developing the perovskite solar cells. So you could see from the North Carolina, North America, South America, and also China, and also Sweden also have the Linkso, led by my supervisor, Dr. Feng Gao, and also many other commercial efforts from other states. And with so many efforts to put our perovskite solar panel to the real world application, actually one thing that I want to raise before is that all the high efficiency or high performance perovskite solar panels contain the so-called lead ions. It's different. It's different from other lead containers that the perovskite material contains these lead ions, and these lead ions can be dissolved in water. So if we put this kind of solar panel in the kind of in this kind of ground, and if it's broken or unintentionally dropped into the water or other things, these lead ions can enter our food chain, like it can go into the water flow and then accumulated by the fish, and then this fish or the water can finally reach our human, and also, or it can go to the soil, and the soil can pass the lead ions to the plants, and then it can also accumulated by our humans. So the lead ions is I think is a very big concern. This is a very typical example for the numbers. So for 1 gigawatts perovskite-based solar system, it contains around 3.5 tons of lead. And if you compare to the paints or soil, the lead concentration is strictly forbidden, limited. So like the paints used in our daily life, the lead concentration should be below the 90 ppm. That's part per million. And if you talking about the drinking water, it's 5 parts per billion. So it's kind of strictly forbidden or strictly limited for the lead ions in the daily life. But if we have the perovskite-based solar system with so many lead, it's a big concern. So actually, there are many works have been done before I develop more, before I trying to solve this problem. So the lead management, it's a I think it's a very big topic that has been raised by, I'm not sure the name, but Thomas or something. So some typical work have been published is that they can do the on-device light capturing. So they use some encapsulant to physically forbidden to block the light ions to get out from the perovskite module. Or can also be light recycling. So this one is a very typical example for the light recycling. So they dissolve the degraded solar panel and then use some cations exchange resin, and then use some chemical process to extract the lead ions, just the lead ions, to get the recycled lead, and then react with the sodium iodide to get the lead iodide, and then use it to fabricate the solar panel, new solar panel. But in this lead recycling, actually most other ions have been kind of discarded. We think it's not enough, but it's already the best work that has been reported at that time. And we have to know that the solvent that has been used in that process is DMF. It's actually a very common solvent that has been used in perovskite processing and also recycling at that time. But DMF is a very typical organic solvent. It is hazardous, and we will talk it more. So previously, when I tried to realize this lead problem in perovskite solar cells, the first work I'm doing is how to reduce the lead leakage in perovskite solar cells. So usually there is a physical blocking that, as I explained before, uses some like encapsulant physically blocking the lead leakage, or it can introduce some chemical absorption that's using this kind of lead absorbing materials, and then if the lead ions are trying to escape from the perovskite solar module, this will block or it will capture escape the lead ions and then to block the lead leakage. So at that time, we are trying to think about whether we can develop an encapsulant that can have both this function. That means we want the physical blocking and we want the chemical absorption to get the light safe perovskite module against the extreme weather conditions. So this is a work that we have developed, the PAA glassy gel. So how to improve the mechanical property that we have published in this Nature paper. And then, so we use this PAA glassy gel to modify the function of the polymer chain. So usually the gel is the polymer network that was swollen in the organic solvent. So we firstly modify the polymer network with this kind of carboxyl group. So this carboxyl group can coordinate with the lead ions and then to capture the lead ions. And also we choose the ionic liquid with this phosphate acid group to both can be coordinated with lead ions, so it can both the polymer network and the ionic solvent can coordinate with the lead ions to have the lead absorbing property. So this is the typical lead absorbing kinetics that we have measured. So this is showing that we newly synthesized the PAA energy gel could capture the lead ions efficiently. So we want to use this energy gel as an encapsulant for the perovskite solar module. So we tested the mechanical performance to trying to know whether this PA energy gel can be a physical blocking encapsulant. So as it's a gel, we can have it make it like to be stretchable. So we have the strain to be around 500%, and the module that we can tune to be very suitable for the encapsulant And more importantly, we have the self-healing property for the encapsulant. So this is a demonstration that how we use the self-healing. So we firstly cut two different PA energel, two energel samples, and then we choose one of this one to put it together and put it under 50 degrees C for 2 hours, and then it's self-healed. And if we use this self-healed sample, we can find it can be stretchable again. So to show how the PA energel can be a very good mechanical improvement for our perovskite solar module, we can use this one. So usually we use the glass for the encapsulant, and you can see for the bare glass, it can be easily shattered into pieces. And if we use the glass with energel, so this is glass, and we have a layer of energel on top, so it can now be resistant to the the metal ball dropping test. And we have tested for more than 15 times. Sorry, yeah, for more than 14 times, and then it finally break. But our energel can still make the sample to be intact. That means it will not break into pieces. So we incorporated this energel into encapsulation to test we firstly tested the efficiency, because we don't want this encapsulant to be very damaging to our perovskite solar modules. And we found it can be very good for efficiency and stability. It can be compatible to our high efficiency and stability. So we use this for the lead leakage test. So what we are doing for the lead leakage test is that firstly we use the metal ball to hit the module, that is to break the module, and then it's to simulate the hail test, like the snowing or raining or other things, to break the solar module, and then we put the degraded or not the broken solar module to the water and soaking it as it's flushed. And then we are trying to test the lead ions concentration in the water to see how many lead ions have been leaked to the escaped from the module to the water. And we compare the three different structures. And this structure C is the one that using our aerogels as an encapsulant. The other two are copying from like the structure A is a typical thin film solar panel. The structure B is the using for the silicon solar panel structure. So this is the image from the soaking module that are soaking in the water for 24 hours. And from the lead concentration in the water, you can see that the structure A and B is the typical encapsulant with a typical structure. The lead leakage is kind of very quickly to the hours to saturation actually. But for our structure with aerogel, it can remain almost no net leakage for 24 hours soaking. Actually, it's because this health test do not break our solar module. So we're trying to do it more against a more extreme condition. We use a car to go over to our solar module. So this is a pristine sample. We put it here, and then we use the car to go over it, and then to break our sample. It's too slow. Maybe, yeah, so it's a zoom in. So you can see the bricks, and also it's very clear bricks. and then we put the damaged module to the water for soaking again, and this time we extended the time to 45 days, and we could see the change of the color. Actually, the change of color means how many perovskite has been dissolved or kind of damaged by water. And now this time we could see from the this kind of yellow change, color change for our aerogel-based encapsulant. But for the lead leakage test, we could see it's still around 3 orders of magnitude lower than commercial one. So we think it's a very good lead leakage against the lead leakage encapsulant for our aerogel. So it's very exciting for us to kind of handle this lead leakage. But when I went to Linköping to do more research on perovskite solar cells, I'm thinking about what I can do more, or is it enough for perovskite solar module to enter the market? So the first thing that we think is that we have to learn from silicon PV. You know, it's already a very established solar panel industry for silicon PV. So in 1 gigawatts PV was of silicon PV was installed in around 2000. It's the first time that the world have this PV system, and now it's around 2025, but actually 13 years ago, the EUWEE is the waste of electrical and electronic equipment have this kind of directive for PV recycling. This directive have asked the solar panel producer to pay for the solar panel recycling. So they have to handle their waste. And although the directive was kind of reported and initiated until 2016, around less than 1% of the waste solar panel had been recycled. Even most of them have been actually landfilled. Just find somewhere that has not been so strictly forbidden. They just put it into the soil. Even some of them were recycled. What they are doing is just ground the module and collect to small pieces and then put them as a fillers to the building concrete. It's kind of waste. It's so-called down cycle. So the value of the solar panel is not well recycled actually. So now around 2018, actually 2018, it's the recycled value is kind of increasing, but it's still not that high for PV, for silicon PV. What I'm talking about, just the silicon PV. So actually, it's a number that I got when I trying to search for the perovskite PV. Is that when we at 2023, if a silicon PV producer trying to solve their waste, they have to pay $30 to recycle per panel, but they just have to pay $1 to put it to landfill. So it's easy to choose which one to dispose the waste, but it's not very good. So even even at this time, the low cost and high value recycling for silicon PV is still under development. This is because the silicon PV is not, they need the high purity single crystal, and they are so brittle, and it's difficult to grow the single crystal again with so many impurities. And yeah, so many technical difficulties in silicon PV, and now it's not easily to achieve. So, But for our perovskite PV, what lessons that we can learn from the silicon PV is that if we want to put our perovskite PV into the market, we should have a solution for the perovskite PV waste before we put it into the market. Otherwise, we will face the same problem of the silicon PV again, and even worse, because our perovskite PV waste contains the lead ions. We can't just put it to landfill, and the lead ions is water soluble. So we should get an optimal recycling technique for perovskite PV before we put it into market. So when we think about how to recycle the perovskite PVs, we definitely want to get the best. So for the technical parts, we need to get it feasible. Firstly, we need to get a high recovery yield, and also we want this technique to be scalable and also reliable. But for the economic part, we need this process to be profitable. That means we can make money from the recycling. Otherwise, no one wants to waste money for recycling. At least the motivation will not be that strong. So we have to control the processing cost. And also we need the product to be high value. But for the society part, we think we need to minimize the environmental impacts. And also we need to minimize the health risks. So we need to combine them all in one sentence, that we need to get a reliable, high-value recycled product with pollution-free recycling. Yeah, it's very challenging actually. It's kind of we want this, we want that, we want all. So this come back to the topic that was presented before, that we propose the holistic recycling for sustainable perovskite PV. So we want the solar farm, perovskite solar farm, to produce energy to the power company and then supply energy to our society. And this society will consume more energy. But when the solar farm is at the end of life, the degraded perovskite solar panel like this one with this layer by layer structure can be layer by layer recycled actually. So what we are trying to do is that we recycle the cover glass, we recycle the perovskite, we recycle the perovskite, and then we recycle the tin oxide and also the ITO glass. And then we use the recycled materials to build a new module with pollution-free recycling process. We want to make the whole process to be pollution-free and high efficiency. Then we think only in this way it can be called a sustainable perovskite PVs. So how we achieve this? So for the recycled cover glass, this is easy. We just use the heat to soften the EVA, because the glassy transition temperature for EVA is just around 120. So we use the 150 degree C heating to soften the EVA and then mechanically detach the recycled cover glass. And then we are trying to recycle the perovskite. So what we are doing is that after we detaching the cover glass, we dissolve the degraded module with hazardous-free and low-cost solvent, that's acid acetate. And then we use some reductant, that's aldehyde ions. And then we also found that this solution has some EVA residue. So we use the filtration to remove the EVA and use the anti-solvent, that's the ethanol, to recrystallize the perovskite, and also after 2 times of washing, we got this high purity perovskite. So with this process, we use the hazard-free and the low-cost solvents to achieve the high recycling ratio, more than 97 weight percent of the spirometite. And also the spirometite that we recycled is neutral, it's not doped. So we tested the recycled spirometite is the with the compared with the fresh spirometite, the device efficiency almost the same. And then we come to the main part for the perovskite. Actually, because the spirometite is not very difficult to achieve, but it's very we have to handle it very carefully. But for the perovskite, what we want is we have to get a low cost, high value, high yield, and generalized, and make it waste free and pollution free. This is difficult because no one has done this before. And what we are doing is that, so we want to make use of the solution process, definitely. This can be very low cost. But when we search the article, when we search the published papers, all of the papers using the DMF, DMSO, GBL, these are common solvents for perovskite processing. But they are so expensive and hazardous. For example, the DMF, it's kind of very strictly limited in the working place, less than 10 ppb. So it's difficult to use DMF for recycling. If you want to recycling, then you want to make some benefits for the environment. But if you use DMF, you are getting more burden for the environment. So we want to use some water, because water is the most green solvent and also maybe the most the cheapest solvent. But when we try to dissolve the perovskite into water, we found the solubility of the lead iodide in water is not good actually. It has only 0.044 gram per 100 milliliter. So that means if we dissolve the perovskite like the MAPI, it's a typical perovskite composition, the methylammonium iodide can be easily dissolved, but the lead iodide, it can be dissolved, but the solubility is different, very different. So if we want to do the recycling, the first thing that we need to solve is how to dissolve the perovskite completely with water. So one thing, one strategy that we used in our technique is that we use the so-called sodium acid, or we were trying to introduce the acid ions to coordinate with the lead iodide to compete with the iodide ions, because we found that lead iodide has the limited solubility, but the lead acetate has almost 1,000 times larger solubility in water. So you can see from the picture, maybe more clear, if we dissolve 10 gram MAPI powder in this water solution, it will have this yellow lead iodide residue. But if we add more sodium acetate ions into the solution, this lead iodide residue can be easily dissolved. And then another thing that we are trying to solve is that we are dissolving, or we are treating the degraded perovskite, not the common perovskite. So we need to fix the degraded perovskite. So first thing is the IL2 is the most common degradation product in perovskite solar panel. So we are trying to introduce the reductant in the solution, and then to reduce the IL2 to be iodide ions. And then we trying to combine them all to the perovskite recycling. So it's not just the dissolving, right? We have to dissolve, repair, but the final thing is that how can we get the perovskite from the water solution? we actually tried the drying process before. That means we just evaporate the solvent, we get the perovskite powders out, but we found this can introduce more impurities because we add so many ions, the sodium ions, the acetate ions, and also the reductant. And this drying process will make the recycling process non-reusable. That means we cannot use this solution for another recycling. And also we are trying to searching for the anti-solvent method. It's also a very typical method that has been used for perovskite crystal growth. But unfortunately, we didn't get any green anti-solvent available at that time. So we are thinking about whether we can just make it self-precipitate. That is, we just heat the solution at 90 degrees C or even higher, and then we cool it down to get the crystals. Use the solubility difference at the different temperature. Then we can get the crystals. It's very native thinking at the beginning. But when we trying to do this, we found what we get. Even we combine these two additives of the sodium acetate, the reductant, we still get the lead iodide precipitates. It's not the perovskite that we want. So then we are thinking, what's wrong with it? We search for the literature. We found actually the lead ions, the lead iodide, have this the edge sharing structure in the solution. So if you have the edge sharing structure in the solution, what you will get from the solution will be the lead iodide. But the perovskite phase is this kind of corner sharing. If you have this corner sharing, that only one iodide ions has been shared by two lead ions. So if you want to get the perovskite phase, you have to firstly make the lead coordination to be corner sharing. And the key to control the sharing mode is to supplement the iodine ions inside. So if you increase the iodine ions, you can control the sharing structure to be phase sharing, edge sharing to corner sharing. So then we add the third additive, that is sodium iodide, as we show here. And the motivation is just to introduce the iodide ions. And you can see here from the absorbance, when we increase the iodine ions inside the solution, we can clearly see the appearance of the lead S3. That's the structure for the corner sharing of the lead ions coordination in the solution. So we combine them all to the three additives are trying to solve three different problems. That is the solubility, phase purity, and also the stability issues in the perovskite solar module. And combine them all, we can now recycle the perovskite with just the water solution. This is how we demo the recycling of the solution with water. This is the pure water solution with the three additives. And then we can put the perovskite films into it. And if we remove the perovskite later, the substrate later, and we cool it down, the perovskite crystals can self-precipitate very quickly. And also we checked the crystallinity and also the quality of the perovskite. It's high quality because it's a kind of crystal growth process. We also extended this process or technique to different perovskite compositions. We found for FePe, it's easy to recycle, and also we try to recycle it for the FePe and MePe 1-to-1. It can also be used. And also we're trying to demo that whether our technique can repair the degraded perovskite or not. So we recycle the FePe with deficient FAI inside, and it can still be good. The recycled film can still be a good crystallized perovskite film. And also we recycle the FePe with excess I2. It can still be a good perovskite film. More interestingly, that we use the multi-round recycling for reliability. That means we recycle the degraded perovskite module, and then we use the recycled component to fabricate a new module, and then the new module will be degraded again, and this is one cycle, and then we do this cycle for 5 times, and then compare the device efficiency. It can be comparable with fresh one. So the most important is that how this process can make benefits for our environment. So we do the environmental impact assessment from the power generation, material production, and also heating, how we get heating, cooling, and to do to simulate how we process the perovskite solar module and for the encapsulation, how the electricity was generated, and then do the recycling. So it's a life cycle assessment for the whole process. And we found that actually I'm not quite familiar with so many parameters. So I choose two for that can be very easy for us to identify the importance. So one is the human toxicity related to cancer. So with our recycling process, the human toxicity related cancer can be degraded for 68.8% compared to landfill if we landfill the perovskite solar module. And also for the material resource depletion, it can definitely be even more important, that reduce 96.6%. So it can do very, very good for the environmental benefits. Yeah, and also the compared to silicon is also a very good one. So yeah, that's all about the work. And yeah, it's very deep. It can't be complete with the supervision from Professor Feng Gao and also the support from Nian Shen, who is the main leader for the spiral omitted recycling, and also the Tian Kai, and also other from the support from Fengqi You, Professor Fengqi You from Cornell University and their team, and also the simulation test from the Professor Yan Fa Yan. Yeah, thanks.